December 1958. A satellite's radiation counter suddenly flatlines, not from failure, but from something too intense to measure. That satellite was Explorer 1, America's answer to Sputnik. Physicist James Van Allen expected a steady trickle of cosmic readings. Instead, at certain altitudes, his Geiger counter went dead silent, overwhelmed by radiation far beyond anything scientists had predicted. What Van Allen had stumbled onto wasn't a malfunction. It was a hidden structure wrapped around our entire planet, two donut-shaped zones of charged particles, trapped and accelerated by Earth's own magnetic field. Today we call them the Van Allen belts, an inner belt dense with high-energy protons and an outer belt thick with fast-moving electrons. Together, they act like an invisible shield, protecting the surface, but menacing anything passing through. For NASA in the 1960s, that shield became a problem. Every crewed mission to the moon had to physically fly through this radiation, a gauntlet no human being had ever crossed before. Engineers ran the numbers obsessively. A capsule's aluminum hull offered some protection, but not much. Prolonged exposure could mean radiation sickness, damaged tissue, even elevated cancer risk decades later. This wasn't science fiction, it was an engineering constraint with human lives attached. So NASA's solution wasn't better shielding, it was speed and precision. Apollo trajectories were plotted to punch through the thinnest, least intense regions of the belts at the fastest possible velocity, minutes instead of hours. Timing mattered as much as the path. Launch windows were chosen partly around this crossing, threading astronauts through a region where the intensity dropped just enough to keep exposure within survivable limits. There's also a strange gap in the belts, over the South Atlantic, where Earth's magnetic field dips closer to the surface. It's called the South Atlantic Anomaly, and even today, low-orbiting spacecraft, including the International Space Station, briefly pass through elevated radiation there. So how much radiation did Apollo astronauts actually absorb crossing the belts? Estimates for a typical lunar mission put total exposure at roughly the equivalent of a few dozen chest X-rays. Uncomfortable, measurable, but survivable, thanks to that narrow, fast trajectory. Some astronauts reported something even stranger during the journey, brief flashes of light behind closed eyes, even in total darkness. Cosmic rays striking the retina directly, a silent reminder that they'd left Earth's shelter entirely. For decades, the belts have also fueled a persistent myth that they were simply too lethal to cross, supposedly proof the moon landings never happened. It's a claim built on ignoring the actual physics. The danger was never absolute. It was about duration and intensity, not a wall of instant death. A fast trajectory through the thinner regions kept doses within limits doctors had already deemed acceptable for short-term spaceflight. That doesn't mean the risk vanished. Future missions changed the equation entirely. A journey to Mars means months, not minutes, exposed to deep space radiation, a challenge engineers are still trying to solve. In 2012, NASA launched twin spacecraft, the Van Allen probes, specifically to study these belts up close. They discovered the belts aren't static at all. They swell, shrink, and sometimes split into three distinct zones. They found something else too, so-called killer electrons, particles accelerated to nearly the speed of light during solar storms, capable of frying satellite electronics in an instant. It's a humbling thought. The same invisible structure that once threatened to fry a handful of astronauts on their way to the moon still governs how we design every spacecraft we send beyond low orbit today. Van Allen himself never called them a hazard to be defeated. He saw them as a discovery, proof that Earth was stranger and better protected than anyone had imagined before that satellite went silent in 1958. The astronauts who crossed those belts didn't just travel to another world. They punched a hole through an invisible ocean of radiation that had wrapped this planet since before life crawled onto land. It's a story rarely told in the highlight reels of the space race, not the flags, not the footprints, but the quiet, calculated gamble made just to get there alive. If you want the untold engineering gambles behind every space mission, subscribe. There's a new hidden story from the history of spaceflight every week.